In Learning Objective B, we're going to talk about the multiplication counting principle, which allows you to figure out how many elements are going to be in a group without having to draw a tree. And what it says here is if you have groups A and B, where they're finite sets, so it means there's a limited number in each set, then you can figure out the ways to choose different elements from them if you just take the number of A times the number from B. So if we go back to Pete's Pizza, again, Pete has two different choices he's going to ask you. He's first going to ask you, do you want cheese or pepperoni? So that in itself is what we want for the topping. There's two choices. The second question they're going to ask you is what kind of crust do you want? Thin, thick, or stuffed? And there's three choices. So all you do is they show in this formula here, you multiply those together, and you're going to get that there's 6 choices. This is the multiplication counting principle. There's another counting principle to keep in mind. One is if you have a string where you can actually have replacement take place. And here's what this means. The formula they say is n to the k power, where n stands for how many elements you're choosing from, and k is the length of your string. So if we look at this example, I'll show you how it works. It says how many strings with replacement are there of length 2 with 3 different symbols to choose from, A, B, and C. So imagine you have a bag with the letters A, B, and C inside of them. And you're going to make a string with length 2. So I'm going to have to make 2 choices to fill in. So maybe I'm making an answer key. If I put my hand into the bag here and I grab a letter, I have 3 choices for that. So the first grab is 3. Now what this one says is you can have replacement. And they mentioned it here, you replace it. So let's say I grab the letter A. I'm going to put that back into the bag. So when it comes to my second draw, when I go back in for the second drawing, I'm going to pick a letter. All 3 letters are still there. So now there's still 3 choices. Multiply those 2 together, just like it's the 2-letter string, and you get 9 choices. So the difference here now is you have to ask yourself, when you make the second choice, is there still going to be 3 in the bag, or is there really only 2? If you can replace, there's 3. If you pick a letter from the bag and you don't replace it, then this would only be 2. So you have to read the question carefully and know what the scenario is. So in this example, it looks like we're looking at the game Wheel of Fortune, where we have a spinner divided into 24 congruent sectors, numbered as we see at the right. You cannot land on the boundary lines, and we're going to spin it twice. So determine the sample space for this experiment and determine the number of elements in it. So the number of elements in the sample space we're going to spin twice. So I have spin 1 and spin 2. And they didn't say anything about replacement, you just have to be logical. So the first time you spin the wheel, we're going to have 24 different choices, which goes here. Now the second time we spin the wheel, how many choices are there going to be? Can you replace or no replacement? Clearly the wheel still has 24 segments and you can land on all 24. So it's going to be 24 again. Multiply these together, there's 576 different outcomes in the sample space. I can describe the sample space, I'm just not going to write it all out. So we could have, for example, 250, 250, 500, 250, 500, and 100, 100, and 500. There's 576 different ways you can spin that wheel. Now we're looking at the same example, but now they want us to spin the wheel 3 times. How many different outcomes are there? Well, 3 spins to the wheel, 24 choices on the first, on the second, and on the third spin. So what that one theorem said is you'd say how many choices you have, and then how many times you're doing it. 24th to the 3rd power. I personally just do the space method and fill in the spaces versus memorizing theorems to use. It's very obvious to me that 3 of these 24s is the same as 24 cubed. The answer here is going to be 13,824. Now, what is the probability of each individual outcome? There's only one unique outcome for every scenario, so the probability is 1 out of 13,824. Now let's look at this one. A lottery game played in some states involves picking 3 digits from 0 to 9 in order. So we're going to pick 3 digits, digit 1, 2, and 3, and we're choosing from 0 to 9. Describe the sample space for this experiment and determine the number of elements in the sample space. So you need to think about, it's a lottery game. They've said nothing about if can we have repeats or not, and so we would want them to clarify it more unless it's something we had to figure out. If they are picking, let's say from different bins, they have the numbers 0 through 9 for number 1, 0 through 9 here, and 0 through 9 here. When you pick for your first choice, be careful, there's 10 choices. The second bin, there's 10 choices, and the third bin will have 10 choices. So there's going to be 1,000 different outcomes for this particular lottery game. Let's do a more advanced one. We have a 28 question multiple choice math test, and there's 5 choices for each question. How many answers could there be for the answer key? Well, I'm going to start doing, question 1, 2, 3, question 28. I don't want to put all the spaces here, but there's the questions. And I just think about it. Well, question 1 for multiple choice, there's 5 choices. Of course you can have repeats. If the first answer is A, the second could be A. So question 2 has 5 choices. Question 3 has 5. And it continues to go until I get to question 28. So what the answer is I have 5 28 times. And that's going to simplify to a very large number. This here is how many different ways you could answer a 28 question multiple choice test if there were 5 answers each. And if you look at this, how to even say this would be hundreds, thousands, millions, billions, trillions, quintillions, and quintillion. Now, part B asks you, if you randomly guess on each question, what's the probability of getting all 28 questions correct? If you think about an answer key, how many answer keys would a teacher have for this test? 1 answer key. So the probability is going to be 1 over this entire number. I'm just going to put 5 to the 28th power since it's such a long number. Here's another scenario. How many ways can you answer 3 multiple choice questions that has 3 choices and 2 true and false questions? What would the sample space look like? Well, just think about it. We have 3 multiple choice questions and then 2 true and false. Each multiple choice has 3 different choices. The true and false has 2. Now, a lot of people will get confused right here. They think, should I add or should I multiply? Think about it in terms of the answer key. If you were doing this on a Scantron, would you do a separate Scantron or is it just one continuous Scantron? Well, it's one continuous Scantron, which means it's one continuous string, which means you just multiply these together. If you multiply this together, you're going to end up getting, there's 108 different choices for this answer key. And I want to show you what they look like. Again, people will get confused and they'll tend to just do this number, which is 27, and then they'll add this number and say 4. You'll say there's 31. That's wrong. Here's what they actually look like. This here is all 108 different ways an answer key could be filled out for the 3 multiple choice and 2 true and false questions. Okay, let's continue on. A license plate. We have a license plate that has 2 letters followed by 4 digits. The digits can be 0 through 9. So I'm going to say the first 2 letters, and then we're going to have 4 digits. It's one long string. There's 26 letter options in the alphabet. Now it's a license plate. Be logical. Yes, you can have repeats. They're not going to tell you that. There's 26 for the second choice. Same for the digits. 0 through 9 is 10 digits. On license plates, definitely have repeats of numbers. 10, 10, 10. You multiply this out, there'll be 6,760,000 different license plates you can make with this type of combination. Now here's an interesting question. We're going to piggyback off of the answer we got on the previous slide. So we know that the number of license plates that we could make that were 2 alpha and then 4 numerics was this, 6 million and some. Here's the question. Suppose each license plate is equally likely and that your family has this license plate. So we have that license plate. It's guaranteed. It's already been used. What's the probability the next car you see either has this license plate or this one right here? Well, think about the entire sample space in this case. The bottom of our fraction will not be this number exactly. It will actually be one fewer because we already know our license plate. So that's not in the group anymore. What's the probability the next license plate will be one of these two? Well, it's going to be 2 out of the 6,759,999. Let's look at one more. Here we have a license plate with 3 letters followed by 4 digits. So we're going to do 3 letters and 4 digits. In this case, assuming that we can have repeats, we'll have that scenario. And then we're going to have 4 digits. If I wanted to write this, I could have said it was 26 3 times 10 to the 4th power. If you multiply that out, we're going to get 175,760,000 different license plates can be created if we just add one more alpha field at the beginning.